Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this specific video, we will be discussing about another amazing concept in machine learning, and this is all about boosting algorithms. Um, I have seen that there is very less content available on YouTube with respect to boosting algorithm, but this is one of the most powerful algorithm if I'll talk about in machine learning, solving so many complex problems, uh, whether you're talking about banking domains or any of the risk specific domains. This XGBoost kind of algorithm, or nowadays, yeah, XGBoost is very widely used, but obviously to understand that as well, that AdaBoost gradient boosting plays a very important role. So in this specific video, you will find out that that's a recording of my paid ML bootcamp, which I have organized few months back. So what I am explaining in that bootcamp, you will able to observe in that specific classes the intuition behind boosting algorithm. You will observe that I'm talking about the difference between bagging, boosting, and stacking. This is one of the most important interview question, very widely asked in a lot many product based companies. Afterwards, you will observe that I'm talking about the mathematical intuition of AdaBoost, and in the end, I'm showcasing whatever be the mathematical intuition I have given to the learners, the implementation for the same. Because until or unless you don't know how can we implement the stuff, I feel the knowledge is half, and that's of no use, right? So please make sure that you will watch this video till the very end, although the video is of longer length, and I will try to attach the timestamp of the video in the description of this part. One important request before we will jump towards the main session is, I am seeing the stats of my YouTube, and it's very disheartened that many people who are watching the content have not subscribing to the channel. See guys, without your support, it's very impossible for me to reach to wider audience. So I think your single click button and your single comment will really enhance the performance of this channel, and it will help me to reach to more wider audience, and that's the I think main goal for us, right? So please make sure that before jumping to the next session, where I'll try to attach the recordings of my class, you will hit like button, share this video with everyone, and comment it down that whether you have understood the concept or not, or is it helping you all or not. If you do that, definitely I will try to upload more recordings where I will try to talk about gradient boosting algorithm. I'll talk about XGBoost internal maths, and definitely this kind of videos are that much in-depth intuition are not available. I have done a lot of research. I'm referring one book also in the class that I will share with you, as a reference, which you can also refer. So all these things, please, are coming for free for you all. So please do a bit from your side also, and it really means a lot to me. With this, let's get started. So let's start our journey today with respect to the boosting algorithms that we have to discuss today. Till so far, we have talked about two different types of ensemble techniques. What are those? Till so far, we have talked about in our curriculum two different types of ensemble techniques. Can you tell me the name of that? What you have learned?
Mem staking.
Stacking, okay. And bagging, right?
Yeah. Back.
So, till so far, if you guys remember, in our ensemble techniques module, we have explored majorly two components. One is bagging, another one is stacking. Today, for the very first time in our entire course, we will be focusing on boosting. One of the very widely asked questions in interviews is that what is the main difference between bagging versus stacking versus boosting? We will discuss that question today and how basically you have to answer that particular question. But before jumping towards that part, definitely you should know the core idea behind this boosting algorithm and how it works. This algorithm says you will see in every website, in every standard book, one common line that what we are doing in boosting is we are trying to combine all the weak learners and forming up a strong learner altogether. So, what is the meaning of that? Let's try to understand this with a very layman example. Let's say कि we will be having, like I'm teaching in this class, right? And currently in my class, let's say 10 students are there, right? I am giving you guys, let's say 5 questions for machine learning. Okay? I have given all of these 5 questions to all the 10 students who are available in my class. If that is the task I'm doing, that I'm giving all of these 5 questions to all the 10 students simultaneously, and parallelly, every student is doing its own task. This technique is called as bagging, if you remember. In random forest, what we are doing? Randomly samples picking up without replacement, sorry, with replacement, and decision tree is going on simultaneously. Parallel processing, something is going on, right? In boosting, what is happening is that I'm not giving the task of all the 5 questions to the entire students. What I will do, first of all, I will say that I will give to the student S1. Okay? I have 10 students. What I am doing is, I'm not giving all the questions to all the students. I am saying, first of all, I will give all these questions to student S1. Now, let's say student S1 has done maybe 2 questions correctly, but somehow third, fourth, and fifth question, he has done it wrong. But 2 questions that student has done it correct. Now, what will happen? What will happen is that I'm giving these wrong conclusions which student S1 made to the student S2. And I'm saying that can you solve these problems? Let's say student S2 is able to solve third correctly and fourth and fifth is wrong. Let's suppose. Okay? Fourth and fifth is wrong. So this is a correct version, and fourth and fifth is wrongly done by student S2. Now I am saying that okay, fourth and fifth is wrong now. Then I am giving to S3. And let's say S3 mein fourth question is done correctly, but fifth is again done wrongly. But fourth is done very much correctly. Now again, what is happening? I am giving this question to student S4, and now fifth question is also done correctly. Now at the end of the day, I have all the correct results, but it is not done by single student. It is done by the accumulation of student S1, S2, S3, and S4. And that is something is the core idea behind the boosting algorithms. That's why it's called boosting. Boosting. All algorithms which are individually weak learners. What is the meaning of weak learner? Simple meaning is that S1 alone will not able to perform well. But when I will combine all of these weak learners, means S1, S2, S3, and S4, it will be able to perform a very good result. It will be able to give me a very good result. Means it will be able to form a strong learner with accurate predictions altogether at the end of the day. That is the core idea behind the boosting algorithms, right? One thing which you will be able to observe here, parallel processing is not there, just like the way we had in a bagging technique where we are passing all the random samples all together with replacement in all the models that we have. In boosting, what is happening is at a time we're just passing to one model. So just replace this thing with a model M1, M2, M3, and M4. So now we are passing the training data to model M1. We will get some result. We will first of all evaluate that result. And the result which is wrongly classified, or you can say wrong result, is there. That is the one which we are passing to the model M2. And this is how things are going on. And that is why this is something which we call as a sequential learning, which is going on in the boosting algorithms. Till this part, is the analogy is clear to everyone what I'm trying to convey? Any confusion anyone is having, whatever I have conveyed here? Any doubt?
So, how the model is improving in the second S2 basically, the errors.
In S2, we are just somehow focusing more on, wrongly classified points. There is a concept in boosting algorithm which we will discuss in the upcoming part of the today's session, called as weights. So how it is correctly classifying in the upcoming case is that what we will do is, somehow for the wrong classified points, we are increasing their weight value, and for the correctly classified points we are decreasing the weight values, decreasing the weight values, which somehow giving the indication to the model M2 that okay, I don't need to focus more on this part. I just have to focus on this wrongly classified points wala part and try to do a proper judgment of that. So there is a lot of weightage thing which will happen internally. There is a lot of maths also we will discuss in the upcoming part, where we will start today our very first algorithm named as AdaBoost, or adaptive boosting. So when I'll discuss the maths behind that, you will get an idea that how is this happening. Okay. But this is the core idea. This is how things are happening, and that is why you will be able to observe everywhere whenever we had a talk about boosting algorithm. Why they are saying that here we're just combining the weak learners, because every particular model which we are applying is a part of a weak learner which is not performing well. But combining all of them together made a strong result, made a great result. And that is the overall idea behind the boosting technique. Every particular decision tree or every particular model is having a different weightage depending upon how much is the evaluation part they have. If the model is performing pretty well, obviously they will be having a higher weightage as comparable to the model which is you know not working perfectly fine. So that is the core idea behind this boosting part. Before we will focus on the maths behind this ADA boost, one interesting thing, let's discuss that also. Let me just fetch one image. Let's discuss about the maths, the difference between this bagging versus boosting versus stacking. If you can see here, right? If you can see here, we have discussed bagging part, right, in our previous sessions. Whenever we are talking about this bagging technique, one thing which you will observe here is that in that our focus is to reduce the variance. If you remember, we have seen that in a single decision tree, there was a problem of overfitting. Do you remember that? And we have seen that how when we are applying a combination of decision trees named as random forest model, it will be able to reduce the overfitting in our data points. It will be able to reduce the overfitting in the data points. So when I'm saying reduction of a overfitting, indirectly, can't I say that somehow we are reducing the variance in our data? I hope you all know from our initial sessions, overfitting meaning high variance, low bias. So somehow, if I will be able to reduce the variance, that is something which we are doing in a bagging technique, means we're reducing or overfitting in this specific era, in this specific use case. Whereas in boosting, our focus is to reduce the bias. What is the meaning of that? If you remember, when we are talking about this boosting algorithm, we are saying that our model itself is not able to perform well on a training set. That is why it is giving us a wrong result, and that wrong result specifically we are again passing to the model M2. So somehow there is a very high bias. So what I want to do is I want to reduce the underfitting of the model in boosting. Underfitting of the model in the boosting means somehow what we want to do is we want to reduce the biasness of the model in case of a boosting algorithm. Reduce Reducing the biasness of the model. In stacking, we are trying to simply improve the accuracy just by mixing up the predictions, getting the output, passing the different models, getting the output, and that output taking as an input layer for the next layer. That predictions we're taking as an input for the next layer. I hope you remember whatever things we have discussed as a part of a stacking, right? So this is the major difference between bagging versus boosting versus stacking. Another difference will be the base learner types. So if you will be able to observe here, when we are talking about base learner, in bagging, all the models will remain same. If you remember, if you're applying decision tree, everywhere decision tree should be there. If you're applying canon, everywhere canon should be there. In boosting also same thing will happen. You cannot apply different models altogether. But in stacking, you can apply different models. So that is why stacking is a combination of heterogeneous models, whereas bagging and boosting is a combination of homogeneous models. After that, base learner training, as we have seen, it's a parallel processing which is happening. In boosting, sequential thing is happening. In stacking, we're trying to create a meta model. What is meta model? If you remember in our last discussion, we have tried to create a random forest classifier, which is taking input predictions of all of the models that we have. So that is something which you call as a
Multiple
meta
ones.
model, right? In terms of aggregation, in bagging, if the problem is a classification problem, we are applying a max voting. If it's a regression problem, we are applying a averaging. Whereas in boosting or in stacking, we are working on the weighted average part, right? In both of them. So we will see that how weighted averaging is working in boosting in the upcoming section of the video where we will talk about the AdaBoost. But this is the core idea, this is the core intuition behind the difference between bagging versus boosting versus stacking. Is that part is clear to everyone? Is all these differences that we have covered up with respect to the purpose, all of them have a different purpose altogether with respect to the base learner types, with respect to the base learning training type, and the aggregation, how we are trying to combine the results, because anyhow all of these three are a part of ensemble technique, means multiple machine learning models are working. So how can we combine those results to get the appropriate result, appropriate answer, appropriate prediction altogether? Makes sense to everyone? If it is fine, so with this, we can, I think, start a very first type of boosting algorithm, which was very first originated in the machine learning called as AdaBoost. The full form of AdaBoost is adaptive boosting. So what we will do for the very first part is we will try to see the mathematical intuition behind this algorithm. We will try to focus on how this works internally. Again, there will be a bit of maths. Please don't get scared. I will try to explain the mathematical portion in a very layman manner. But still, if you get any confusion, any doubt, you can, at that point of time itself, just pose me and let me know that I have to revisit that concept again. I will try to, take that concept again and will try to explain you again. Okay? So, is everyone ready? Shall we start the concept of AdaBoost if the introductory part of boosting is clear to everyone? Shall we start? Can we use it for both supervised and unsupervised dataset? No. So whatever be the ensemble techniques we are discussing, this is only be useful in the supervised module. It's a part of a supervised machine learning algorithm. So it's only be useful for the supervised technique where you will be having a labeled data, whether we are talking about bagging, or we are talking about stacking, or we are talking about boosting. So for unsupervised, only the clustering algorithms that we have covered up will be helpful. I hope it answers your question, Prasanna. Any other doubt anyone is having? चलें आगे? Also, whether you're talking about bagging, stacking, or boosting, one more question you can ask from me with respect to what Prasanna has asked. Maybe if someone is having that confusion also, so let me clarify that all of these techniques in supervised also will be useful for uh, classification also and regression also. So in sklearn, we have a separate modules of both of them, classifier and regressor. So you can implement both of the tasks. So useful for supervised and in that too, in both the tasks, classification as well as regression. Okay? Okay, let's move ahead now. And let me insert one more image. And again, whatever images I'm inserting here, it would be good if I will give the credit to the book itself. I'm taking all these images from the book, which I think you all know. What is that book? So let me just open that from where I'm picking up these things. So this is the book. Okay? Yeah, and this is the complete module from where you can say I am also learning and preparing my content to make you guys understand the things, right? Even the complete ML course, if you will see that, Priya, from where you are referring the things, I will say I'm just referring from this specific book, and there is one cornell lectures which I am referring to prepare my content. So at any phase, at any point of time, if you want to see, refer anything, either you can go with these lectures or you can go with that book. Both of them are the standard resources which you can refer at your end. Okay. Now, if you can see this adaptive boosting, AdaBoost, how it works, things will remain same only. What is happening here? We will be having a training set for now available. So this is the complete training set that we have. Now, what is happening is here the model is working, model M1. By default, it is decision tree, DT1, which is working internally. One more interesting thing in this boosting algorithm, this decision tree is called as decision stumps, where the constraint is that the maximum depth of those decision stumps or decision tree is equal to 1. Why is that so? Because what we want is we don't want the bigger maximum depth based model, which is highly accurate and so on. So, what we want is a weak learner. What we want is the very first intuition in the iterative process where what answer we will be able to get. We're just figuring it out. So, in every of the decision tree, you will observe that by default, that maximum depth parameter is 1 only. So, you will see a very small decision tree in the boosting part. I will showcase you everything in the implementation. So, don't worry. But for now, I'm just explaining you the concept. So decision stumps or decision tree is what is the model which is working internally by default in the boosting part. Now, what is happening is once you will be able to train this model, let's say you will be able to get this kind of predictions. So the prediction is, let's say, this red white line. So somehow you can say it's a classification problem where my model is classifying between two classes. Now, let's suppose that this is something which is a point which is wrongly classified. This is the point. This is the point. So, what will happen is internally you will pass this misclassified point higher weightage. How that will be done? I will showcase you the maths behind that. But for now, you can assume that for all the classified points, there will be a small weightage, and for the misclassified points, there will be a high weightage. And we will provide that specific weightage to the next training set. So, the second iteration, my model will focus more on this data point. My model's purpose is to somehow correctly classify this point. Now, again, you have applied model M2. which is dt2, and this kind of a line you are getting. Now you can see boundary is somewhere different. And again, there will be somehow misclassification of points. Let's say all of these above points are misclassified. So my model will focus more on this misclassified points, and again, we'll try to curate a new decision boundary with the help of model MT, M3, or DT3. Again, this misclassified points, whatever is left, we will pass as a next training sample. Now you can see all the training samples are going, but somehow you can see in this image, some of them are very highlighted, some of them are very low highlighted. There is a color difference, right? Some of them are very dull, some of them are very dark. Dark indicates that somehow the weightage of those points are high. Dark indicates that somehow the points which are dark is misclassified in the previous case. So my model in M2 or M3 is focusing more on those points. That is the core indication. Whosoever has designed this particular graph, I think this is the core intuition which they want to give from this graph. And finally, we will be able to get the final prediction from this specific model, which is the combination of all of these predictions. Now, if you can see, it's kind of a sequential learning only, which is going on, where one model will give us some result. There will be some intuition behind that, some result we will be able to get. After that, again, that particular result, we will take it as M2. M2 will provide some result, followed by M3, and so on. So this is the core idea behind AdaBoost. Is the weight here the same as accuracy? Is the M4 prediction only the misclassified points? First answer, is the weight here the same as accuracy? No. Weight is not same as accuracy. Weight is a parameter which is basically used to distinguish between the classified points and misclassified points. Weightage is a parameter, so it's kind of a cost function, you can say. So weightage, which I'm talking about here again and again, is a parameter which is reflecting the model two things. What are the correctly classified points? And what are the wrongly classified points? There should be some mathematical parameter, no? Otherwise, how my upcoming model will get to know that, okay, this is correct and this is wrong? How this will be done? Just give me a few minutes, everything will be clear to you, right? Is M4 prediction only the misclassified points? M4 prediction will predict any of the points where there will be very less misclassifications now. Means in M4, when you go to the M4 stage, the accuracy will be very high. There will be almost, you can say, very few number of records which are misclassified. So it will be able to give you an appropriate result. And one more thing, in AdaBoost, the results, the classes are of the form +1 and -1. So either the data points belong to positive class or it belongs to negative class. So that is the final prediction which we will be able to get. So in the M4 model, when you are applying a new test set of data, the accuracy will be very high, that it will be able to give you a correct result, that whether the model will belong to a positive class or a negative class. How will it be done? Let's try to go towards the maths behind this. I think then you will be able to get a better idea. Decision stumps are nothing but is a decision tree. I hope you all remember the core mathematical idea of decision tree, where we have seen that how the Gini index or entropy works to curate nodes that we have or to shortlist a nodes. Max depth is one. It means that if you remember, by default in decision tree, we can create, or we have seen in our previous discussions, 4, 5, 7, depending upon how many number of records we have, that many depth part, right? But in AdaBoost, we are saying the depth will be one. Means at max, what you can do is you can curate the height of the tree to 1, right? The depthness should be 1. So that is something which you are saying it as a part of a decision stump. Okay? So just let's try to work upon no, this one. Step by step, I have given you a brief idea what we are doing here. Let's try to take one example and we'll try to understand each and everything in a great detail. Okay? For that, for now, I am just picking up very simple example of 5 data points that we have. I have done already the calculations here on my page, and I'll use those calculations to explain it in a better manner. So let's say we will be having two features, F1 and F2. Let me just try to minimize it a bit, F1 and F2. And these features are 1, 2, 2, 3, 3, 7, 2, 9, 9, 8. Let's say we will be having 5 number of records, 1, 2, 3, 4, and 5. And every particular record is having some output, y, which is 1, 0, 1, 0, 0. This y is the, you can say, actual label, right? Actual label or target, you can say. This is the, let's suppose, original data that we have. This is the, let's suppose, original data that we have. Okay? We have the features F1, F2, and Y. Now we want to apply AdaBoost algorithm in this. Now the question is, how will it work? First of all, we will try to work upon with the maths behind that. Then maybe in the upcoming part, I will showcase you the implementation for the same. Step by step, we will discuss. What will happen is, in a very initial case, our AdaBoost algorithm will find the weight of all of these records. And by default, this weight in the very first iteration is 1 upon the number of records that we have. 1 upon the number of records that we have. For now, we have just taken a number of records as 5. So the value will be 1 upon 5, which is equals to 0.2. So the initialization of all of these records will be 0.2, because initially all of them will be having an equal weight, because initially my model, we have not applied any model. We don't know which is having a correct classification, which is having a wrong classification. Every record is important for me. So the initialization of every particular weight will be 1 divided by number of records that we have. Now let's say you have applied a DT1. First decision stump, decision tree, you have applied on all of these 5 records. Now what will happen? When you apply a decision tree, you will be able to get, let's say, tree like this. F1 bigger than 5, go towards left, otherwise go towards right. F2, let's say, less than 10, let's say go towards left or go towards right. And in every leaf node, you have an answer of 0 or 1. I hope you all remember, right, how the decision tree works. In the last part, we have some classification which is ready with us, which is either 0 or 1. So when you applied this decision tree DT1, you will get some predictions, which is something I'm referring as Y cap. Okay? So Y cap is the prediction given by this model, which is model M1. Right? This is a assumption that this kind of a tree will be made, but definitely it will be something different only. But just to explain you, I have mentioned this. So definitely you will be able to get the predictions of Y cap via this decision tree DT1. Now this Y cap predictions might be, you are getting like 1, let's say this is 1, this is 0, this is 0, and this is 0. This is something which is given to you via model M1, DT1. Here you can see that there are 2 points which are wrongly classified. Remaining are the correct points that our model is giving to us. Right? So what will happen? With this specific intuition, where the 2 points are having a wrong classification, remaining are having a correct classification, new weights will be assigned. There will be a updated weights value which we have, where you will observe that for all the misclassified points, the value will be bit higher as comparable to the values which are having a proper classification done. Now the question is how this new updated weight we will be able to get. But before jumping towards that part, till so far, things are sorted, whatever things we have covered up. Any question? Anyone? Okay. I am assuming then it's sorted. So now, how basically this updated weight will be done? Let's focus on that part. There is something called as a alpha parameter in the AdaBoost. Now, what is this alpha? Alpha is the, you can say, models say in, you can say, or models performance, you can say. Alpha is the model say, meaning it is somehow inversely proportional to the array. Meaning, for example, if I am saying that I will be having a model M1, and this model is having a error as 0%. It means that in that case, the alpha will be very, very high. Means that model is very efficient. We should listen to that model in terms of finding out the result. Model M2, let's suppose, I am saying 50% error is there. And model M3, let's suppose, 100% error is there. It means that in model M3, alpha is negative. Very, very, you can say low, right? But if I'll ask you that which model is a very dangerous model or which model is having a very high impurity, this is the model M2. It is not model M1, it is not model M3, it is model M2, which is very highly impure. Means here the alpha value is approximately equals to 0. Why? Because I will not listen to model M2. It is very, very impure. Means sometimes it is saying great results, sometimes it is saying vague results or false results. See, in first case, I am happy that my error is 0, means at every point of time, my model will be able to perform well. It will be able to give me the correct results. In the third case, also, I am very happy because I know that it will always give the bad result. So I will do vice versa. For example, if my model M3 is predicting the answer as 1, I will say the final answer will be 0. I will do negation of that. But in model M2, I'm highly confused because sometimes it is giving me a correct result, sometimes it is giving me bad results. So I will not rely on this model M2. So with this, if I have to plot a graph between this value of alpha and this value of error, so let's try to see how this graph will looks like. Let's say in the x-axis we have error, and in the y-axis we have the value of alpha. Okay? So when the error is almost zero, my alpha is very high. Means in that case, my model says very, very high. Means I should have to ask from that specific model. That model is very important to me. My error is, let's say, very high. Let's say it's 100% means the value is 1. In that case, the alpha value is negative. I will maybe take the negation of that answer. It's negative. But if my error value is 50%, means zero point 0.5, in that case alpha is 0, means I will not take any say from that model because that model is highly confused, right? It's like you have 3 friends in your life. One friend always say truth. So you will say that it's a very reliable friend of mine. He or she is my best friend because they always say true. Whatever I will ask from him or her, they will always give me the correct answer. Then you have another friend who always say lie. That is also somehow good. Why? Because Whatever he will say or she will say, you will say, I will do vice versa, right? Because whatever they are saying, I will do vice versa, because they are somehow, I know their nature, they will always give me a false result. They will always give me a lie answer. But let's say you have a friend where sometimes he or she will give you the truth, but sometimes they will give you a lie. So you don't have trust, right, with respect to that person. So in that case, maybe you will not rely at any point of time to that specific person. Same thing is happening to the model also. Now, when we will try to plot this graph, this curve looks like this, going from here to here, and then from here to here. This is a kind of curve, although I'm not able to represent it properly. Let me try one more time. Like this, and then like this. This kind of curve is coming up. And in maths, this is a curve for the equation of logarithmic 1 by 2 natural log of 1 minus error divided by the error. So this is where you will be able to calculate, this is the curve of this equation of alpha. Now, what is this error? This error is the addition of all the misclassified points. This error is the addition of the weightage of misclassified points. So if I will say, in my very first iteration, how much is the error? You will say 2 points are misclassified. What is the weight of that? 0.2 plus 0.2. So in my very first iteration, if I have to calculate the value of alpha 1, so it is 1 by 2 natural log of 1 minus 0.4 divided by 0.4. And with this, you will be able to evaluate the say of model M1, which you just now have built. And it is nothing but 0.6 upon 0.4. And if you will just solve this equation, I have solved it few minutes back, it is coming out for me 0.20. So this is the value of alpha 1, which you will be able to calculate. Now, why we have evaluated this part? To update the weights. Do you remember? We have to update the weights. So, for all the correctly classified points, for all the correctly classified points, if you remember, I told you we have to somehow decrease their weightage, because what I want in second iteration, my model should focus on the misclassified points majorly. So, for all the correctly classified points, my updated weight will be the current weight of my model into e to the power of minus alpha 1. This is the alpha 1, which we have just now evaluated. And for all the misclassified data points, the updated weight will be the current weight into e to the power alpha 1. Is that fine till so far? Now what we will do? What is the current weight we have for a model? It is 0.2 into e to the power minus of 0.20. If you evaluate this term, it will come out to be 0.16. And if you will evaluate this specific term of 0.2 into e to the power of 0.20, it will come out to be 0.24. So now what will happen? For all the correctly classified points, your new weight will be 0.16. And for all the misclassified points, your weight will be 0.24. Now ask me the questions if you have. Here we didn't use it weight for misclassification. We have used Prasanna. We have used. See this and this. We have used the weights for both of them, but the formula is changing with this factor. And if you will see the graph of this e to the power negative and e to the power positive, you will get the intuition that how, in this case, we are we are having a value of the updated weight as lower than the current weight, and how in this case we're getting a higher than that. Point 4, we are reducing in first case and increasing in the second case. How is that so? I can showcase you this thing. Uh, Let me just showcase you visually. Let me open this particular tool. Let's say I will say e to the power x. Okay? So can you see this graph? It is increasing. Can you see? It is increasing exponentially. But if you just write e to the power minus x, what is happening? It is going towards the negative direction. It is decreasing. So just try to compare these two graphs. Y is equals to e to the power x. So here, this blue one indicates e to the power x. So we are saying e to the power alpha, e to the power minus alpha. So when you're saying e to the power alpha multiplication, you're going in a positive direction, means you're increasing your value. But when you're saying e to the power minus of x, you're decreasing your value. And that is the main reason why for the correctly classified points, we will be able to reduce the weight value. And for the misclassified points, because we're multiplying with e to the power of alpha 1, we're increasing the weight value. And that is something which is the updated weight that we have for our next iteration. Now, what we will do with this updated weight, I will talk about that. But for now, let's take a pause and let me ask
Yeah,
a question.
yeah, yeah. The last part, can you explain a bit after we find the misclassified data points
Huh?
and the correct data points? How you are arriving to these numbers updated weight?
This part is clear.
Yeah, this part is clear. Correctly classified points and misclassified points. But
Point
after
one
that,
six, how it comes, and point 24, how it comes, it's clear to you, right?
huh? Yeah.
So
I mean that
now, in this
this we
case,
have to kind of this formula we have to mug up, right? This e to the
which one?
power. Uh,
Yes,
okay.
yes. Like for getting a better understanding only, I have just showcased you the reason behind this maths, where this
Understood.
graph, that graph, right? How that value is decreasing in negative alpha 1 and how it is increasing in positive alpha 1. So once you will be able to get this number of 0.16 and 0.24, the updated weight for correctly classified point and misclassified data point, what is happening? You have two records which are misclassified. So for that, you know the weight is 0.24. Just now you have done the evaluation. And for the remaining, you can see the actual and the predicted. This is predicted. They both are same. 1 and 1, 0 and 0, 0 and 0. It means for them, the weight is 0.16 because they're correctly classified. That is the reason.
Okay, understood. Okay. And just one query exists in mind, that
Huh?
equation is equation of a log graph. So
Hmm.
that we don't have any clue, right? I mean, it's like we have to remember this also. This.
Yes. See, there are in mathematics multiple graph plots, and for every graph plot, we have a separate equation, right? For example,
Mhm.
exponential, logarithmic, natural log. Similarly, with respect to this kind of a curve, researchers come up to a point that this curve seems to be similar like this equation. And that is the main reason why they have used this equation, which is this
Mhm.
logarithmic of 1 minus the error rate, where this error rate somehow represents the weightage of the misclassified points, the summation of the weightage of the misclassified points that we have. So that is where they have you use this value of alpha as a parameter to update that weights. How they're using that? Via this calculation, which I have just now showcased you,
Yeah.
right?
So it's like
Uh,
lambda is equal to 1/2 of that one, right? Logarithmic of 1 minus error
1
by error.
minus error upon error. Yes, correct.
Sure. Thank you.
Okay. Any other doubt anyone is having? Just give me a second. I'll just take my water bottle back. Meanwhile, you can just see if you have any doubt, you can just let me know. Yes, so far so good. Now, if you will see the addition of these updated weights, right? This addition is not equal to 1. It is approximately 0.48 plus 0.48. It is equals to 0.96. But what I want is, I want to convert that into normalized form where the addition of all of these weights will be equal to 1. So what will happen is, it will try to convert that into normalized weight. How will it be done? It's a simple maths. How can we normalize these weights? 0.16 upon 0.96 into 100. So normalization will happen, and you will be able to get the values as 0.166, 0.25, 0.25, 0.166, and 0.166. Now, if you will add these numbers, you will be able to get the answer as 1. So what we have done is, we have simply converted our updated weights to normalized weight so that the addition of all of them will be equal to 1. And finally, I will try to convert this into one specific range of weights. Where what I will do, I will say it will start from 0, ending will be 0.166. Then further it will be 166 to 0.416. So I am specifying a range. Now, how I am specifying? Again, a simple maths I am using here. Let me write it down first. 0.666 to 0.832, 0.832 to 1. Anyone, any idea how it is done? It's very simple. What is the first value? It's from 0 to 0.166. Then just add these two numbers and take the ending value. It will be 0.416. Then add these two numbers, these three numbers. It will be 0.666. Then add all of these four numbers. It will be 0.832. Then add all of these numbers. It will be 1. So what we have done is, we have converted this weight value, normalized weight value, into specific ranges. Till so far, is that thing is done. This table is clear to everyone, starting from F1, F2, Y, getting the weight, getting the Y cap via the model DT1, updated weights, how we are doing, normalized weight, and the range. This complete table is clear. If any doubt, any confusion, you can ask.
Ma'am, how you are calculating the normalized weight, ma'am?
How we do the normalization in maths? I want
Ma'am,
the addition
yeah.
of all of these numbers to be 1. So I have to do normalization. So in mathematics, how the normalization is being done? I'm asking one question.
Generally, ma'am, we will take the floor or ceiling value, ma'am.
Generally, what you
Generally,
are
we will
saying?
take floor or ceiling value, ma'am.
No.
And we
Whatever
can
number you have, for example, if this is 0.16, acha, without, let's me open the calculator in the laptop. I was just opening in my mobile phone. So
use min max normalize.
here, in this normalization, what we are doing, whatever value we have, 0.16, divided by, what is the total value you have? 0.96. So what is the value you're getting? 0.166. So this is the value I have written here. Similarly, you can do for all of the values. So when you do this task, what will happen? Intuition behind the weights will remain same. But now, if you will do the addition of all of these weights, it will become 1. That is the simple way or technique in maths to do the normalization. If let's say you have some numbers and their sum is not equal to 1, and someone said to you that, can you normalize these numbers so that the addition will combine together, will form up 1. Even in naive bayes classifier also, normalization came into picture in the ML machine learning algorithm. So if someone says that normalize these numbers, can you normalize this? For example, you have probability values and somehow that addition is not equal to 1. Can you normalize these probabilities? So what you will do, you will take that probability number divided by total number which you're getting as a sum. So when you do that, the addition of them will become 1 in the normalized case. Is that fine now?
Yes, ma'am.
Any other doubt anyone is having? Is this range is fine? How it is coming up for everyone? So far, so good. Shall we step up then? Now, what we have done till so far, let me give you a brief summary before we move to the next iteration so that things will not be jumbled up in your head. What we have done till so far, we had the training data, or you can say train set available. We have passed this train set completely with a same weightage of all the points available in the train set, which is nothing but 1 divided by the number of records that we have. We passed it to a DT1, which contains the maximum depth as 1. Now this DT1 will be able to give me the predictions as Y cap. Now I have compared these predictions with Y. I got the result. Few of them are the correctly classified points which I got, and few of them are the misclassified points which I got. Initially, I was having the same weightage, but now I have to change this weightage because in my next iteration, when I will, work upon DT2, I want my DT2 to focus more on this misclassified data points because this is the main worry points which we have. For that, we have seen the curve between the error and the value of alpha. And the curve looks like a mathematical equation, which was alpha is equals to 1 by 2 natural log of 1 minus error upon error. This error is nothing but is the summation of the weightage of misclassified points. We have done that. And then we have tried to update the weights by saying whatever be the current weight of my model that I have into e to the power negative of alpha. For example, if you're using DT1, it's alpha 1 because every time for every iteration, for every model, we have separate alpha because we have separate error altogether. For misclassified points, it was the current weight into e to the power of alpha 1. We have seen visually also that when we are multiplying any term with negative of alpha or negative of x, so that number is depreciating in the graph, whereas in case of positive alpha, it will appreciating, means the number will increase its value. And that is what we want. And that is the main reason why researchers have used these equations to increase the value of misclassified data points and decrease the value of correctly classified points. Once we have the updated weights, we have observed that there is a problem, that weights are not normalized, means they're not adding up to 1. So we have normalized those updated weights and convert them into a specific ranges. Now, till so far, this is our journey that we have done in the boosting algorithm. What will happen in the next iteration? My model will randomly pick up the data points now. So we have 5 data samples available. I will say to my model, pick up 5 random samples or pick up random values of the range that we have, above range that we have. So this range is from 0 to 1. So in other words, I am saying to my sample points that pick up 5 random values in the range from 0 to 1. And that is the main reason why we have normalized the weights also. So what will happen is it will pick up, let's say, 0.42. It will pick up, let's say, 0.31. It will pick up, let's say, randomly it is picking up. There is no logic here. 0.60. Let's say it will pick up. Next point is maybe 24. It will pick up 0.90. Now, what will happen is all of these points belong to some record. For example, 0.42 belongs to this specific range, and this record belongs to third record, third sample in my data. 0.31 belongs to this specific range, and this belongs to my second sample. 0.60 belongs to again 3. 0.24 again belongs to 2. And 0.90 belongs to a sample 5. So for the next iteration, the sample which will go is 3, 2, 3, 2, and 5 for the training part in the DT2. This is the training sample which will go. It will take 3, 2, 3, 2, 5. Now, what is the intuition behind this thing? It's very interesting. Try to understand it. You will get my point. We know that the points which are misclassified points will be having a higher weightage because this is how the maths is being done internally. And we know that for those specific points, the range will be very, very high. So the chance of getting the random values or the probability of getting that samples will be very, very high. And that is why you will be able to observe this 3 and 2 are the misclassified points, and they're coming up very high as comparable to the sample as 1 or 4 or 5. Is that intuition is clear? So what will happen is, in the upcoming case, your training set, when you pass this, your training set, the new training set will contain the samples frequently as 3232, and maybe there is some other sample with it, maybe 5. It can be anything. But you can imagine the situation when we will be having, or we are dealing with a very huge amount of data. At that point of time, obviously, for the misclassified points, we have a huge range, huge corpus. And when randomly data point will come up, probability of specifying in that specific range will be very, very high, obviously, because the range is very, very big. So that is why automatically what will happen in your next iteration of a train set, you will get more samples which belongs to misclassified points in previous iteration. And that is the main magic of this weights part. That is the main core idea of converting that values into the range and then transferring that. Now, same thing will happen again. Again, DT2 model will run. Again, Y cap will be there. Again, we have a Y value. Comparison will happen. Alpha 2 will be evaluated. Then the next value is doing the updation of the weights for the classified and misclassified points. Then again, after updating the weights, normalize that, getting that range, and then same thing will pass to the DT3 and so on. So is that transformation from the samples from DT1 to DT2, is it clear to everyone? Or is there any confusion? That how smartly, when we take a random samples of the number of records that we have, for example, here we just have 5, so we are taking 5 random samples here. What I'm trying to convey here is that for the misclassified points, the range will be very, very big. And if the range will be very, very big, in that scenario, the probability of getting those misclassified points will be very, very high as comparable to the correctly classified points. That is why Automatically, if you have more samples which belongs to the misclassified points, your model will be more inclined towards or biased towards focusing on that misclassified points rather than focusing on the classified points. And that is how this boosting algorithm works. That is how why I was saying that in this specific diagram, wherever misclassification of point will happen, in the next iteration, my model is focusing on that dark circle more as comparable to the light circle. Although the number of training samples will be same, but the focus will be shifted towards the misclassified points. How is that so? Now I have showcased you the maths behind that. Is that making a sense to you guys what I'm trying to convey here? Ask me the question if you have before we will move ahead.
Hey, Priya, I have a question to understand better. Until the random number generation, I'm very clear. And we generating a random numbers to classify group of ranges. That I understand. So now we have a group 3 to 5 is from the five records. When we go to DT2, should I consider only those records, or what will be my input set, train
So
set
in your
when we
DT2, you have 5 samples only, just like the way you have in DT1. But in this case, you have 3 samples, 2 samples belonging to class 3, 2 samples belonging to, means there is a repetition of records. Can you see that?
yeah.
In total, you will be having a 5 records only. But there will be the probability of having repeated records of misclassified points will be more as comparable to correctly classified points, because my model already correctly dealt with 1, 4 and 5th record. Focus should be on 2 and 3. So you will be having a duplicate records for the misclassified points in the next iteration. So in DT2, you will be having this record as a training set: 3, 2, 3, 2 and 5. 1 and 4 will no longer be there.
Okay, still it is going to be 5, but still there are duplicates with the same records, same fields.
Yes, yes.
Okay.
Okay.
So what if the random number generation, maybe is there any mathematical intuition or anything we can use it to generate the random numbers?
Anything you can use it to
Okay,
generate the
if
random
I use
numbers.
if I use any logic, and then in case if it gives me the group from 1 and 4, that not belonging to the misclassified category. So what will happen in that case?
In that case, your model will not work well. The model evaluation or the evaluation metric will not be good. Means at the end, when you perform testing on that specific model, definitely that problem is not resolved. No,
Correct.
this problem is not resolved, so your model will not perform well. But the chances of the probability of happening this is very very less when you are trying to get the randomly generated data points. See, here for now, for explanation purpose, I'm using only 5 data points, and that is why you cannot see the bigger ranges also in this case, right? The difference, although it's also big, for example, 0 to 0.1 is very small, whereas 0.1 to 0.4 is very big. 0.4 to 0.6 is a very big as comparable to further ranges from 0.666 to 0.832. But still, the variation is, I would say, not that much bigger number. But when you will be working in your real time data with a very huge number of records, this range shifts is very, very big. Means for the misclassified points, the gap will be very, very big as comparable to the correctly classified points. So when you are trying to get, let's say, 1,000 or 10,000 or 20,000 randomly data points, chances are very very high that maximum number of times, almost 80% times, it will fall under the categories of misclassified data points. And yes, 10-20% times which you are talking about, that it will fall under the uh, correctly classified points ranges. And that is the main intuition, and how, that is why I think this algorithm is still working well in lot many situations, lot many scenarios. But considering your question, that if that situation will happen, let's say we will be having a limited data points, and my model randomly is not picking up 2 and 3 and will picking up 1, 4 and 5, what will happen? Definitely your model will not perform well on that data, and either you have to change your model altogether or you have to reiterate your model altogether on the complete data set, right? Does it make sense?
Got it. Yeah, got it.
Any other question anyone is having? One more important thing. So the same thing will happen. Now you can ask me question. No, nobody asked, but I was expecting someone will ask from me that Priya, how many number of times we will perform this similar task? You said that in DT2 down the same thing will happen. Now let's say we will be having DT3, DT4. Now how will we get to know that how many decision trees we required? So again in this also we have an estimator called as number of estimators, which is an hyperparameter uh, in our AdaBoost algorithm. But for now, let's assume that it is 4. For now, let's assume that it is 4. Or let's say it's 3. Okay? Although for big data points it is 100, but for the explanation purpose, I'm saying let's say it's 3. So how at the very end, let's say you have applied DT2 and again same procedure you have applied, and then you have taken the further data points and you have applied DT3 also, and then you got some predictions. So the question is that how will we combine all of these 3 predictions? So at the end, your final prediction, which you will try to evaluate at the end of the day, which is y cap by the last model DT3, you will see the sign of alpha 1 h1x plus alpha 2 h2x, or you can say alpha 1 y1 cap plus alpha 2 y2 cap plus alpha 3 y3 cap. So basically you will try to see the prediction of individual model that you're getting for that new set of data point. You have DT1, DT2, DT3. You will check the prediction of all of these 3 models that you have in your data, DT1, DT2, DT3. You have the value of alpha 1, alpha 2, alpha 3, which will indicate a say of that specific models. And then when you combine these 3 results, either your result will be positive or negative. If it is positive, means data belongs to a positive class. If it is negative, means data belongs to a negative class. And this is how the entire classification of data points is being done in the boosting algorithm of AdaBoost. So at the end, we're just combining all of these results. That is why we are combining all of these weak learners. Alpha 1, Y1 cap is a single weak learner. Alpha 2, Y2 cap is a single weak learner. Alpha 3, Y3 cap is a single weak learner. If you will see the combination of all of these 3 results and combine together and then check the symbol, whether it is coming out to be positive or negative, that's the complete core idea behind the classification part of Y cap. If it's a regression problem, you will not see the sign, you will just merge them up and you will be able to get some continuous number. That is the final prediction that you will be able to have. Does that make sense to everyone? Whatever things just now I have conveyed to you, shall I showcase you step by step practically what is happening? See, although it's similar to the previous models, which I usually say, see, in every model, I'm trying to showcase you the internal maths. Chances are very low that people will ask you the internal maths of specifically AdaBoost or PCA in industry when you will go to the implementation per se. Interviews, they can ask. But in the implementation, when you will do the projects, I don't think you will require this kind of a knowledge in depth, right? You will definitely from sklearn, there is a AdaBoost classifier. You can directly call that. Number of estimators by default is 50. You can do hyperparameter tuning. You know how can we do that? Grid search CV and randomized search CV. You can perform that and you will be able to get the amazing results altogether. No need to even consider the mathematical intuition. Nowhere it is in depth mentioned also in the documentation that how is this working. But why I'm teaching you all of these things? Because somehow, first of all, for the interviews perspective, this maths is important. Secondly, I feel that as a beginner, we should always start from learning towards the intuition behind every algorithm, how it comes up, because nowadays everything is a black box. If you will ask from industry professionals that how these algorithms are working, they will say it's a black box. Don't worry about this thing. Even if you can try with your manager, chances are very high. The people who are very experienced professionals, they don't even know the maths behind the things. They're just worried about the development part, getting the results done. Will that be done or not? They will not appreciate much towards the mathematical part. But if you want to go towards research side, want to publish the research papers, you will see that in every research paper, a deep maths is related. And this habit you can achieve only by studying it like this only. That you should know the maths behind every algorithm. Then only, obviously, in future when you do your own research, or you want to curate new model, or you want to do some changes in the original model of AdaBoost, then only you can do, right? Then only you can make some open source contributions. Otherwise, if you don't know the maths behind that, how will you perform that? So it really depends person to person. Now, I'm not saying that it is mandatory for everyone. If you are someone who likes to build stuff, don't care about how internally things are working. For example, when we drive a car, there are two kinds of people. One person who wants to know the internal behind how we can drive, how the accelerator is working, how the braking is working internally, how we are changing the clutch internally, right? How the things are working. There is another kind of a person who says that I don't care, I have a comfort, I have a AC on, I have a song on, I just want to drive a long drive car. Who cares whether it's Audi or it's a BMW? I don't care. I just want comfort level in a car. I don't know the internal things behind that. I don't care also. Same thing happens in technical side. If you are someone who wants to see whatever things you're using, what's the internal intuition behind that, this is something which you have to focus. If you're someone who is in a very good position, managerial level, and who thinks that, why is this required to learn? By SQL calling itself, I can able to implement the stuffs. So it's okay. It's okay. Maybe you can just focus on building the stuffs and getting the task done at the end of the day. It really depends on you. But I would personally recommend, it's my choice. I think I'm biased towards, uh, learning to in a way that first of all we should know the internals about that, and then we should move towards the implementation side. And that's why I think I'm a mentor also. If from the starting itself I don't have a intuition that okay, I should know this stuff from maybe book referring, YouTube lectures, I might not be a mentor today, right? So somehow everyone has its own interest and everyone has its own way of learning. But this is something which I usually like, right? So uh, this is something which I am guiding you as well, whatever I'm doing here, right? So whatever steps we are doing with respect to small data points that we have, let's try to cover up those steps in the implementation step by step. And then maybe I will also showcase you at the end of the day that if you want to do it on your own with respect to this calling just sklearn AdaBoost classifier, how will it be done? Both of the aspects. But that we will see at the end, because there is nothing big which we will crack here. But this is something which is very, very big. You have to understand that how the things are working internally with respect to whatever things we have covered up till so far. So, shall we start this discussion? So let's connect this file, and I have taken random data points here. You can see we will be having a set of 10 records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 records available. X1, X2, and I will be having a labels also available with us. So let's make it as F1. This is a feature 1 that we have to make it more understandable. And this is the feature 2 that we have. And this is the final target column that we will be having, right? Now, you can see that feature 1, feature 2, and target. I hope you know this plot, scatter plot, to just to see the relationship between these two features depending upon the Hue is a parameter which usually tries to do a classification based on the target value which we have. So if you will be able to see, because you are using this hue parameter, you will see two different points will be there, 0 and 1, and different colors are there. So you can see one is available as a blue color, and sorry, one is available as a orange color, and 0 is available as a blue color with us, right? So feature 1 and feature 2 is available with us. Now, let's say we want to do a classification task by applying a AdaBoost. I'm not using any default sklearn package here. I'm doing it step by step because just now I have showcased you the maths behind that. So, the very first thing is to get the weights. And in the initial case, the weights is nothing but 1 divided by the number of records that we have. And if you can see the shape of our data for now, it's a very small data, 10 cross 3 means 10 number of records we have, 3 columns we have, F1 and F2, and last one is the label one, target one. So what we are doing, we are taking a shape of 0, means we are just focusing on the number of records that we have. So the weight will be 1 upon 10, which will be 0.1. So we are attaching this new column by the name of weights, where every specific column is having a weight of 0.1 available with us. Now, what we will do, next task is to train our model, DT1, and getting the value of y cap, so that we will be able to see how many misclassified points are there. So what we are doing, we are importing decision tree classifier, DT1. This is also called as decision stump, where the maximum depth is equals to 1. I have told you prior itself. Now we know in the X part, what we want as an input feature is these two records, feature 1 and feature 2. So we are taking all the records, 0 and 1. And Y is the target column, which is the second column that we have, which is 2, right? So we have taken these values. If you want, you can just verify what this X contains is the two features that we have, 1, 5, 2, 3, and so on. And what this Y contains is the target label that we have, an array of 0 and 1. Now you're applying the first model that we have, which is DT1. Done. And let's try to plot this DT1. So you can see maximum depth is 1. That is why we're able to get this kind of a picture, right? We can clearly see, depending upon this decision tree classifier, definitely we will be able to now get the predictions apt, right? So you can, if you want, plot the decision regions, and this is how your graph looks like. So here you can see in this graph, there are somehow 3 misclassification of points that we can see, right? This square one, can you see? 3 squares belonging to class 0 should be downward the line, but they're above, right? This is the issue. So let's try to see it exactly what are those records. Just check the predictions. So now you will be having a Y-pred available with you. Can you see that? Now, can you verify 1 and 1 is fine, 1 and 1 is fine. This is the first misclassification. This is fine, this is fine, this is fine. Second misclassification. This is fine, this is fine. No, this is not fine. Third misclassification. So we have figured it out with the diagram also. There are 3 misclassified points, and with the actual numbers also, that there are 3 misclassified points that we have. So if I'll ask you, what is the error in this case? What will be your answer? If I'll ask you, what is the error in this case? What will be your answer?
0.3, ma'am.
0.3. Just add the weights of those 3 misclassified points. So it will be 0.1 plus 0.1 plus 0.1. It will be 0.3. What is the next task? Evaluation of that alpha value. So this code is basically helps us to evaluate the value of alpha. What is that? 0.5 np.log 1 minus error upon error. Now we will pass the value of error is 0.3. Just now you have told me. So with this we will be able to get the value as alpha 1. Once we will be able to get the value of alpha 1, we have to update the weights with a value of alpha as 0.423. Now this is interesting. if the labels are correctly classified. What is the meaning of that? If the label and the predictions both are same, multiply the original weight with a e key power minus alpha. Otherwise, multiply with e key power plus alpha. That's what I have done. And now we have applied this in the new column. So, okay. This is not label. In our case, it's target. So let's change the code a bit. And now again, recheck it again. So now we will be having a updated weights available with us. Now, one thing you will observe that for all the misclassified points, the value of the weight is bigger, which is 0.152. And for the correctly classified points, the weight is smaller, which is 0.06. Initially, everyone was having a same weight of zero point 0.1, but now in the updated weight, for the misclassified points, we have a bigger value. For the correctly classified points, we have a smaller value. Till so far, it makes sense to everyone? With me? Everyone? Can you guys give me the confirmation? Seems easy now? Whatever things we have covered and whatever implementation we are doing? Similar? Everything? Any doubt? Anyone? By the way, these explanations you won't find on public platform. So please make sure you will be able to understand these things in a very great detail. Okay. And even if you will start reading, like the people who are not in the live session, and let's say they will say, "Ki, let's start reading from this book about boosting part." And let's say they will start reading this. By looking into these stuffs itself, they will give up, right? There is a lot many things which you will feel ki it's not making sense at all. But now, if after working upon this session, things will be very easy to understand that why that alpha term is coming up, what is the intuition behind that. Because in books also, many things the writer usually don't write. They assume that people know already. But for the people who are not from a math background, right, everyone is not a mathematician here or is not done a masters in mathematical part, they won't be able to understand that how that error term is coming up, how that curve is coming up. So step by step, things won't be clear to you guys. And that is why reading a book might be a tedious task for many people. But that is why I think these kind of sessions will come up in between. The mentors will come up where they will teach in a way that things will be very easy to grasp. And that's the core idea, right? So please listen it very carefully. So now what is happening is we have analyzed the weight of this updated weights and we have figured it out. It is not equal to 1. So what we have to do? We have to evaluate a normalized weight. So how we have done? I think I have showcased you that what is the current value divided by what is the summation of that value, which is 0.91. And with this, if you will implement, you will be able to get the normalized weight. If you will add the addition of these normalized weights now, it will be always equal to 1. You can just verify and you will be able to see it is 1. Now, what we want is the next step is the range of the numbers, right? In this range of specific numbers, how can we define? It's very simple again. Upper and lower value, the range of that. What is the upper value? The addition of the cumulative sum. What is the lower value? Upper minus the normalized weight. It's very simple. So just apply that maths and you will be in a situation where you will be having now finally feature 1, feature 2, target, weights. So this is the same table which I think I have drawn in my lecture. For a 5 sample data points, it is for 10 data sample points. So here you can see we have updated weights. Then we have a range of that 0 to 0.071, 0.071 to 0.14, 0.14 to 0.03, and so on. One thing which I have missed is to showcase in this table is normalized weight. That was also a part of my table in the session. So let me take that factor also into account. So now this is the table which is ready with us. Is this table is looking fine to everyone? This is similar to what I have curated this F1, F2, Y weight, Y cap, updated weight, normalized weight, range having 0 to like lower value to upper value. Same thing, exactly same. Makes sense? Shall we work upon creating a new data points now randomly? If everything is till so far pretty much clear to everyone, because now we have a range of numbers. Now the next point is to curate a new data set randomly and seeing that for which specific sample it belongs to. And then applying a decision tree 2 on top of that. Shall we do? Is everyone with me or things are troubling anywhere? Okay, seems like it is okay with everyone. So let's try to curate a new data set. Now what we are doing is indices where we are storing our randomly generated data points in a list. What we are saying, there is a function of np.random.random. I hope everyone knows, which is basically used to curate a, you can say, randomly points that we have. Now what we are doing is we are just iterating towards the entire rows that we have, taking two values, index and the row, index and the row. So we are saying that if the row value is bigger than a and the a value is bigger than that lower value, so if it is in a specific range, I am trying to append that index. So I'm just checking that if my random value is falling among this specific range, so what I'm doing is I am storing the index of that in the indices list. So what will happen is once you will curate that, you will be in a situation where we can see we have a sample of 0, 1, 2, 3, 4, 8 and 9. So basically you can see the records. So for 2 it belongs to this specific data sample. For 3 it belongs to this specific data sample. So let me do one thing. Let me open this Epic pen and let's try to work upon the, let's see how many number of samples are misclassified and how is the random samples looks like here. So here we will be having misclassified point, this one, and this one. So means 8th one, indices number 6th one, and indices number 2. Okay. Now let's see. 2, 6, and 8. Let me write somewhere. Okay. So misclassified points indices belongs to 2, 6, and 8 as per our intuition. Now let's try to focus again on the randomly data points that we will be able to get. What was that? 2, 6, and 8, right? Achha, this step is called as upsampling. By the way, I forgot to tell you. This step is called as upsampling, where we are doing a creation of a new data points in a way that we are upsample those specific points which are misclassified. So let's see, will that be done or not? So whatever index values we are getting is belonging to 2. 8 is also there. 2 is there 2 times. 8 is also there, but 6 is not there, which is also a misclassified point. But it's okay. It's just the first version of DT1, DT2. Then we will apply DT3 also. But anyhow, whatever points we have, we will start doing the work with respect to that points that we have. and we will curate a second data frame now. So now in this second data frame, you can see we will be having a records of this 029070196 So whatever points we have, corresponding to that, we have the feature 1, feature 2, target, and the weights, right? So we have taken all of these records from that specific original data that we have, which is DF, right? We have taken all the initial 4 records that we have for all the above data points which we are getting. Now what we will do, initially again, same thing will happen now, again, from the very start. Till so far, is it clear how we have done that? Basically, we have tried to curate a random samples which are 10. Although you can see our misclassified points are 3, 2, 6, and 8, but I can see here 2 is coming up in this iteration, 6 is also coming up, 8 is missing, but it's okay. Let's see how it works. We will see how the final intuition will happen. So now what will happen is, for all these index values, we have taken the records from our original data. And now we will perform the same task. What is that task? Creating a DT2, getting the X and Y separation done, fitting that model, plotting that model, and checking the decision regions now, how it looks like. Let's see. Can you say it is far better than the above one, because here there is just single misclassification which is happening. If you will be able to observe here, there is only a single misclassification of points which happened. That is only this one. Remaining, I feel, are apt, right? Are apt. So let's try to see now what will happen further. Let's focus further. Predictions will be there. Second DF data is ready. Now you will be able to see which one is the misclassified point, this one. Remaining all are correct. That's a good thing. Remaining all are correct. So now what will happen? What is the weightage of this? Sorry, what is the error of this particular DT2? What is the error? Can I say it will be simply 0.1? Because only single misclassification happened. So in alpha 2, we are writing the error as 0.1. It is giving us the value of alpha 2 as 1.09. One thing which you will observe, if you remember, in alpha 1, the value was 0.42. It means alpha 1 model, say, is smaller as comparable to alpha 2, which makes sense also. Why? Because in our second model, only single misclassification happened. Remaining all are correctly classified. Whereas in model M1, there were 3 misclassifications. So alpha 2 value is increasing now. That makes sense also. Now accordingly, we will update the rows. Wherever there is a match with the target column that we have, we will multiply it with a negative of alpha, e to the power minus alpha. Otherwise, we will update with the e to the power alpha. And this is where we will be able to get the updated weights now. So you can see we will be having a smaller value for the correct classification and a bigger value of 0.29 for the misclassified points. Same thing will happen again. We will normalize it because it's not a normalized one. We will specify the ranges of that, getting the upper and the lower range, and displaying the second data frame which is ready with us. Feature 1, feature 2, and the target of the second DF. Done. Now what will happen? Again, in the second DF, we will curate a new data set. Now again, same thing will happen. Third DF will be able to give us a new set of records, right? Randomly designed. If you remember, in this second DF, there was just single misclassification which was happened, which is specifically for the 7th record that we have. So here we will be, what happened? It is disconnected. Let's wait for some time. In third DF, again, we are doing the same thing. We're trying to curate a new data set by getting a random index values, 10 random values. Same thing will happen here, but one thing which you will observe, that specific point is not there. Let's see what will happen. So decision tree 3 will be curated, fitting done, and This is where again I think one single misclassification happened. Let's try to see the predictions here. Zero, one misclassification, second one, third one. I think three misclassifications happened if I'm not wrong. 1, 2, and 3. Is it correct? So I think it should be 0.3. Is it correct? So let's try to evaluate the alpha 3. And with this, we will be able to get the value as alpha 1, alpha 2, and alpha 3. Now let's try to check that for the record in the original data 1, 5, the actual target was 1. Let's see what our model is predicting, how we will be able to get the final result. So for the 1, 5, let's try to see dt1. What is the answer? It is 1. dt2, 1. dt3, 1. Now alpha 1 into plus 1, alpha 2, the prediction is plus 1, alpha 3, prediction is plus 1. So we will be able to get the answer as 1.94. What is the symbol? It is 1. Means it will belong to a target class as positive, which is 1. Now let's try to see the another query, which is the record of feature 1 as 9 and where was the original record that we have? Feature 1 as 9 and feature 2 as 9. Target is 0. Let's see what our result will give us as a response. So what we will do here, let's go below. See the result by dt1, dt2, and dt3. So you can see one of them belongs to class 1, remaining belongs to the negative class. So we will combine all of these results. Alpha 1 into positive class, alpha 2 belongs to a negative class, alpha 3 belongs to a negative class. So you will get some response. You will see the symbol of that value, which is minus of 1.09. And this symbol is negative, right? Here also you will try to get the symbol of this 1.94, which is positive. This is the complete intuition behind AdaBoost. So somehow we are trying to combine all the predictions of DT1, DT2, DT3. We are not focusing on a single result. Ki DT1 ne 1 de diya, so it's fine. We are having a final output. No. We are combining all of these weak learners and getting one result. Whatever result we are getting, we are just checking the symbol of that as a final result, that whether it belongs to class 1 or class 0. Class 1 means target is 1. Class 0 means negative number we are getting. So if you're getting a negative sign, it means it belongs to class 0. If you're getting a positive sign, it means it belongs to class 1. And that's the whole core idea behind this AdaBoost algorithm. Now, if anyone is having any doubt, any confusion, please ask. So whatever things I have conveyed mathematically, I have tried to showcase you step-by-step implementation of everything here today. If it is clear, please tell me. If it is not clear, please ask the questions. Otherwise, I think till so far, try to take it for today's class. Maybe in the upcoming session, we will move ahead and see that how via sklearn, that is very easy. It's just a few minutes will require and we will be able to complete that part. And then we will start our next another algorithm in the upcoming session called as gradient boosting. We will see that how that is different from AdaBoost. One more important thing, that to understand the upcoming algorithms of gradient boost and XGBoost, you will be able to understand the maths behind those algorithms only when you know this part. So everything is in a sequence. So don't skip any session. Otherwise, you won't be able to understand any further session. And if you have skipped also, please make sure that before coming to the next session, you will watch the entire recording and you will be comfortable with whatever maths I have shared in the previous sessions. That's the I would say prerequisite to understand the sessions. So far, so good. Do we have to always check the query for all decision trees? Yes. You have to check the query or the output of all the decision trees for that new test set data. And then you have to combine all of these results. That is why it is called boosting. Boost kar rahe hain hum. We are talking about boosting. So at the very end, your final result, as I told you, will be the sign, whatever sign your model is giving, by getting the answer of alpha 1 into the result of dt1 plus alpha 2 result of dt2, alpha 3 result of dt3. Internally, when your model is working, it will automatically do this task where it will combine all of these decision trees results multiplied with the value of alpha. Alpha indicates that how much is the model say. So automatically, whatever model is having a higher say means lower error, that will be getting a higher value automatically when you multiply these two numbers, and accordingly the sign will be decided whether it's a positive or negative.